classes. Okay, so what about the results? So here on the left, we see that we did a few variations on the architecture, just reducing the amount of interaction feature have, okay? So the complete architecture used the two attention modules, the self-attention and the cross-attention, while these other approaches here are just concatenations of the features, okay? And of course you see that if you allow the transformer to blend the features together through the cross-attention, you get a much better result. From 59 you go to 71, from 60 you go to 67, and so on. And if you look at the competing methods, of course this part here is going to have higher values because it works with video, while this is the approaches that only look at the single frame. But still we get, except for this point here, we get the state of the art on this, all these three data sets, okay? Okay, so this work was in collaboration with my PhD student, now he's gone in the industry, unfortunately, Francesco Marchetti, Dr. Morgan from EPFL, Professor Lai from EPFL, Dr. Beccattini, and Professor Alberto Del Bimbo. Okay, so first we have seen how you can work as a human, okay? We don't think about reprojecting coordinates in a word model to understand where other things are, okay? We kind of work like the ego perceptual manner, but probably you have heard this argument about the fact that planes don't use mobile wings, okay? So we need to think about approaches that actually work and solve the problem, okay? So we started collaborating with this company in Sofia Antipolis, and the first thing they told us, they said that you can assume that the map of the world is given, you know it precisely, so you don't have to bother about all the part of the perceptual pipeline. So please just work in trajectory space, and this is what we did for them. So why you would like to forecast trajectories? Of course, they are a company that perform, they do research on autonomous driving, so of course for them it's very natural. Again, trajectory forecasting, it's a natural application to automotive, but I have to say, in general in robotics, the state is a little bit more complex. If you have a human, I mean, maybe even a little bit simpler than the one we have seen before, with 20 joints, you still deal with trajectories observed in the past and in the future, and there is some underlying physics model that can be captured either with a physics informal model or with a deep neural network straightforward like we do here. So of course in an autonomous driving scenario, every autonomous agent has to plan future maneuvers, and they need the future trajectory to follow, but also they need to avoid collision with other agents, so they have to forecast the trajectories of all the other agents, okay? Okay, so formally speaking, trajectory prediction can be seen either in an isolation, okay? You predict the trajectory of a single agent without caring about the surrounding agents. In this case, the most used version of this problem is multimodal trajectory forecasting, where you can observe for each agent a certain amount of locations in the past, usually it's 2 seconds, and then you get to predict a certain amount of futures. This can range from 5 to 20, okay? And these are possible future locations. So you predict multiple futures because, of course, there is a lot of uncertainty, and it is nice to have multiple options, okay, to pick from when you do, for example, planning for other agents' location. Okay, but we are going also to discuss about the problem of social trajectory prediction. Social trajectory prediction is a slight variation of the problem we had before. In this case, when you forecast the future location of an agent, you also take into account all the position of all the other agents you can observe, okay? So the prediction is performed jointly, okay? So you're not just looking at a single agent. You want to update all the location of the agents jointly during the forecasting procedure, okay? And this is probably the best thing you can have on an autonomous driving system, because at any time you're able to say something about all the agents at the same time. and all the agents can get information from neighboring ones. Okay, so this is the example what we are trying to do in a real situation. You have this guy on a bike, and you cannot tell from here if he's going to go left or he's going to go right. Okay, so these are two. I don't know if they are equally likely, but I would say equally likely outcomes of this maneuver. Okay, so. At the time we started doing this, it's a few years ago actually, a lot of models used generative approaches to get a distribution from which to sample the trajectories. Okay? Unfortunately, this kind of approach, specifically for this problem, I don't know what is the real catch there, but what you can observe is that these sample trajectories, they are hardly true multimodal. Okay? So you get this mean trajectory and then a few variation on it. Moreover, it's very hard with the generative model that is somehow estimate the few important modes, okay, of your distribution to manage the long tail, which is very important in autonomous driving, which are those rare occasions in which your model is not covering all the support of the distribution. Okay, so our idea is to don't use a generative model, but use a memory-augmented neural network. So, have you ever heard of memory-augmented neural networks? No? Okay. So, architecturally speaking, it's a simple variation of any other neural network in which you get to explicitly memorize something you extract either during training or during forecasting. Okay? So we will see two ways of using a memory in a neural network. We will feed the memory using recurrent and convolutional architectures, which is important to compute features that are compact. Okay? But the memory is just a matrix of features that we write and read during our inference or during training. So this approach here, as I've written here, is stateful or non-episodic. Okay? This means that after we train the network, the memory will stay still. Okay? So the memory is not used like the LSTM memory, where you update the state during the forecast, and this is a way of keeping up with the dynamics of the system and so on. Okay, so let's see how our model is designed here. Okay? So let's focus on the memory here in the middle. What are we storing in the memory? So the memory is storing some feature from the past concatenated with some feature of the context of the past. Okay? But at training time, the future is known. So what we can do, we can also store future embedding associated with that specific episodes we observe at training time. Okay? So the only problem is decide how to write, which one to write, because the memory is not infinite. You have to keep it small, a few hundred examples, okay? The interesting way we do the multimodal forecasting is directly derived by how the memory works. Because the memory works with a simple attention mechanism, where you just look at the most likely keys for a given observed past and context, okay? Of course, at inference time, you don't get to know the future, okay? So we match, so our keys are past plus context, okay? Our query is the observed past and the context, okay? And the values are the future that we encode at training time, okay? So at inference time, the reading controller will get the top K futures from our memory, okay? And we then perform a concatenation of the observed context and past with the future retrieved from memory, okay? So this way we have possible situations that can happen, but we merge the observed past, the observed future, the stored future with the observed past at current time. And then we feed this triplet to the future decoder, okay? And the decoder is then able to just output different trajectories, okay? Thanks to the way we store data in the memory, the response is usually very highly multimodal, okay? And we will see from the results that when we sample a lot of trajectories, our error goes lower faster than competing methods, okay? So how do you train such a thing, okay? Because remember that the memory will be kept fixed, that will be fed with all these features during training. So first of all, we need the representation to work with, okay? So what we decide to do is to train sort of an autoencoder, okay, where we have past encoder and future encoder and the context encoder to get this feature squeezed in some latent space. The trajectory encoders are GRU and the context encoder is a simple CNN, okay? We try to reconstruct the map and the future alone, so we don't reconstruct the past because we have seen that didn't help at all. After a few epochs of training, you get representations that are sensible for the map and for trajectories. Okay? So once we have done this, we can learn the writing controller. So the writing controller, it's a very simple function. It's a very simple function that is just predicting the probability of writing a feature in memory depending on the error the neural network does at the current iteration. Okay? So during training, we start with an empty memory, okay? And we try to predict future trajectories. If the error is high, we decide that it's important to write that example in memory. If the error is low, okay, we don't want to replicate existing features in memory. So this is I would say, non-parametric, semi-parametric approach at the deep learning problem. So the whole thing we do here is try to learn a few ways to predict this probability of writing in memory additional features. Once we are done with the training of this probability predictor, we wipe the memory one last time empty, and we refeed all the trajectories, okay, so that we can write down the best features for that data set. Okay, and these are a few hundred. Okay, it's not the whole data set. Okay. Okay, so of course we were very worried that reviewers would say that this is just a nearest neighbor. Okay, so what we did is we tried to fidget a little bit with the past encodings and see if something changed into the future. Okay, and indeed what happens here, you can see that if you have a faster past, then you have a faster future. If you have a slower past, then you have a slower future. If you have a random past, then you have a random future. Okay, so somehow the blending of the features happening in the decoder stage, it adds some information to the predictor. Okay, so this was very important to convince reviewers that this was not just nearest neighbor. And we did a similar control experiment that tells you positive and negative things here. Okay, so the original map is that our best trajectory here predicted, top one, is fairly reasonable, close to the ground truth, which is green. And what if we change the map, okay, in something completely different? You see that he likes a little bit more to go straight instead of going right. Okay, but unfortunately, if you just throw a completely zeroed map, you don't get a lot of change in the prediction. Okay, so this also allows to understand the fact that the map is not really important in this kind of problems for some reason. Okay, what we noticed, and we had to devise an additional matrix to the problem to explain this to the reviewers, is that if you add the map, you reduce the amount of time your forecast goes outside of the road, of course, but in terms of errors in meters, it doesn't change that much. Okay. So, what are the metrics in trajectory forecasting? So maybe, is anybody working on this in the room? Okay, so if I ask you, well, how would you measure the performance of a trajectory forecaster? Probably you would go with what we call ADE, which is the average displacement error, which is just the mean square error between the forecasted points and the ground truth points. Okay. I don't like this measure because somehow if you have a very nice predictor making zero errors in the first second and a half, and then goes away. The average displacement error, since it's a mean of all the displacements, it doesn't give you this behavior out. Okay? What I like more is the final displacement error. Okay? Somehow we want to know if our predictor is able to place the object at the end of the 4 seconds, we do in the prediction, close to the ground truth. Okay? And of course you can see from the table, the FDEs are much higher, especially when you do a farther forecast. So for example, in our case, we have less than 2 meters, but if you look at the average displacement error on the same horizon of time of 4 seconds, it's less than 1 meter, because you are averaging all the first steps. Okay, and in my opinion, it doesn't make a lot of sense. But you have to do this because you have to compare with the other guys in the literature. Okay, so we get very good results. We even get this honorable mention at the algorithm challenge. Unfortunately, there were some other methods that were really carved to get very low final displacement error, so we couldn't beat the state of the art for the algorithms, but we did it for this Kitty and also for Kitty and for Cityscape, okay? But still we get this little bit of recognition, okay? We also did some zero-shot transfer experiments. So we adapted these 2 data sets for trajectory forecasting. And this is interesting because our training is outside of the UK. Kitty is in Germany mostly, while Oxford Robot Car, you can tell by the name, it's in Britain. So there are a lot of things different, especially the side on which you drive. But it's interesting to see that the features we extract somehow are intrinsically not really location specific. And once you have the memory fed with the feature extracted from the Oxford dataset, you can still get a zero-shot, very good result in zero-shot setting. So you don't have to retrain it from scratch. This is instead a continual and incremental setting where we start with an empty memory and we feed the features using the learn controller. As you can see, as soon as you move towards more examples observed, the final displacement error goes down and saturates. In the end, you see higher variances because you have very few samples on which you test. So we repeated this many times to get stable results in the end. So this is a very powerful architecture. So memory are very good at zero-shot experiments, and you can easily augment a neural network using a memory. Okay, so this is an approach that should be probably taken more into account when designing neural network architecture. Okay, so code is available. This is a paper from CPR. We extended into PAMI. We also have a patent on it. I don't know if this is relevant anyhow. So if you are interested in this kind of problems, give it a try. There are a lot of forks on this GitHub, so maybe you can start from stuff that is more recent. Okay, so, and this is how it works. You can see that the color of the trajectories somehow is a sort of a likelihood, meaning it's like the similarity. So the darker they are, the more similar are to the input query. And on the frame here, you see the reprojection. Of course, these are, I think, is 10 or 20 trajectories, so there is a little bit of noise. But you see that the long tail, the rare trajectories, like maybe he's also going to steer left, they are captured by our model. We don't have a single mean trajectory with a cloud of trajectories around, okay? So we still get the multimodality that is required by this problem. Okay, so now let's move in a world where communication is more important, okay? So when you are at a cocktail party, when you cross the road, anytime you are in presence of other intelligent agents, you use a lot of social signaling, okay, to communicate your intentions, okay? So I look in your face, maybe I want to talk to you, okay? So if you are willing to, you look to my eyes too, okay? You do eye contact, and maybe we start to talk. But if you are not interested, you may do something like this, and I understand, I say, okay, I'm not going to bother this person. So the idea here is to design a memory, which in this case is episodic, and in this case is also trained end-to-end. Okay? So it's still a memory neural network, but works in a very different manner with respect to the previous one. Okay? So the architecture is pretty complicated, and we will see all, especially the social memory module exploded in the next slides. Okay? But let's give it a little bit of a warm-up now. Okay? So first, the problem is similar as the one before. You observe some past trajectories. These are lifted up into some higher dimensional space. We found that these help, okay? And you have a recurrent neural network that encodes the motion. So at every time step, this will output some token that gets concatenated with some social feature with sigma. And then we have a recurrent decoder. Of course, you know that it is necessary to have encoder-decoder architectures so that you can have different input-output sizes, okay? So the recurrent decoder will output some feature that can then lift it up and transform it into, again compress it down from the lifted up dimension and decode it into future predictions, okay? So for the motion encoder, we use displacements, okay? While for the social memory module, we use actual trajectories. So we decide that the origin is the present frame in which we predict, and then we go backward and we move with respect to the origin. So let's have a look at the social memory module, which is, so these are GRUs, this is gated recurrent unit, so we know how they work. What we don't know is how the social memory module works. Okay, so, okay, so yeah, I think I've said this stuff already. So the important thing is how do you store features into the memory. Differently from the previous approach, this memory is always empty at the beginning of an episode. Okay, so when I start feeding features into the system, the memory is empty. It will read features from the motion encoder, will store this feature inside, and this is a mean of having communications between agent predictors, okay? So maybe it's not easy to see, but this plate here replicates for each agent, but the social memory is a shared set of features, okay? So every pass trajectory, okay, every pass trajectory goes into the weights are shared, but the state of the decoders are not, okay? So for this guy here, you go here, these weights are shared with the other, but the recurrent motion encoder has the same weights, but not the same state, okay? And the same goes for the decoder. But what is always shared is the social memory module, okay? Okay, so first of all, we need to decide how we decide where to read and write, okay? So this is called addressing. So like a computer, when you want to read some values into an array, you start from the pointer, and then you get the address, and you read the feature you want, the number you want, okay? So here, it's a little bit more complicated than that, because we have to learn, okay, a head that is able to perform addressing, okay? So addressing means that we want to compute a vector of weights alpha, and this alpha will identify the relevance of the rows of this memory. We have a recurrent architecture here that for each time step will output this feature gamma, and the feature gamma is used inside this read-write head that has two outputs. The first output is a key that goes by cosine similarity, okay, to search into the memory, okay? So it's searching to the memory using cosine similarity. And on the top, you see there is a different values, that's a scalar value beta, which is actually the temperature that you use for the softmax, okay? So this allows to add an increased degree of freedom in the way these features are interpreted during the prediction, okay? This addressing step is shared between the writing and the reading, okay? So depending on the input you get, this will continuously say what are the important cells that we must look at, okay? Either to read or to write. Okay, so how do you write in memory, okay? And remember that you write at inference time, okay? So this memory is wiped every time you need to do another prediction, okay? It's like the state of the RNN cell. You just have to zero it after you use it for one sample. Okay, so how we work here? So we get the alpha vectors from the addressing stage before, and we have the recurrent memory controller computing the same gamma feature. But here you have the write ahead, which is a neural network which is, of course, outputting the eta and the beta, but it's also giving out two vectors, the E and the A. E for erase, A for add, okay? So once you have computed the E and the A, and this is a standard way of updating memories, so from the original paper from Winston, you see that there's a similar way of doing. You update the memory at the next time step just by combining these matrices E and A. These matrices are computed using an outer product that combines two vectors obtaining a matrix, okay? So this way, the E capital and A capital have the very same shape of the memory. So you can simply do this linear operation to update the memory, okay? Of course, there are learned weights here, so this is not just a simple moving average, okay? So the location you decide to write and read are decided upon the input, okay? So, important thing, since we don't know and we don't want that the order in which the agent access this architecture, since the whole social memory module is shared, we don't want to have any dependence on the order in which we use it. We do the update after a pooling operation on the feature from all the agents, okay? So these are the result of the pooling. So the E and the A are pooled among all the agents, okay? Because the memory is property of all the agents, okay? So all agents read and write the same memory, so we have to update it only once for all of them, okay? We don't want single updates. Okay, so, and finally, to perform the forecast, we do the reading, okay? So again, we increase here the amount of read heads to enable multimodal forecasting, meaning that for each agent, you don't have a single read head, but you have multiple read heads, and these come from different random initialization before you train, okay? So this is a way, very simple way to obtain multimodality. Less elegant than the one before, of course, but still very viable, and in practice it works very well. So here you get your gamma feature. The read ahead has some weights to output the eta and the beta into the addressing stage. And what you do, you just read the features and you do a weighted sum. So this is similar to an attention step. So here we add this future pooling that is required to remove the dimension of the multimodal trajectories, okay? So let's say we are forecasting 5 trajectories for each agent, okay? And unfortunately with this approach here you have to stick with 5 for each of the agents. When you want to go back to the memory, you don't want to have multiple memories for multiple futures. You still want a single place to write. So you pool all the futures together so that you can go back in an autoregressive manner to the recurrent memory controller, okay? So for each future time step, you go back, and at each time step, you get a new prediction, okay? So, at first, we got good results, but we were a little bit frustrated because we couldn't see the real advantage of this social memory module. So we decided maybe the existing datasets do not contain enough social signaling in the data. Why don't we create a toy problem, which is not really so. If you look at other methods that are state-of-the-art, they don't work very well on this like this one, for example, has very low error in other datasets, but here it doesn't work very well. So this toy problem called synthetic social agents, it introduces a very simple rule, which is if I get first to the center of the circle, I get to the right of way, and you have to stop and let me pass. Okay, so this is programmed with random initial points around the circle and random constant velocity for all the agents. Okay, so the only thing that happens is that if I go to the center and one guy is before me, I have to stop, let him pass, and then start again. Okay, so this is the way the dataset is created. As, of course, our approach that is based on the communication between agents has a strong edge versus all the other approaches in terms of displacement error, final displacement error, and also it's very good in predicting the order in which the agents pass. So the Kendall tau is a metric for temporal correlation. It looks if the order of something is preserved. Okay, so in case you work on ordering problems, Kendall tau can be a metric for that. Okay, so what about real data? So we tested on Stanford Drone. Stanford Drone is a dataset made from a drone in the Stanford campus, okay? And the Stanford campus is a mostly pedestrian place. You have bikes, pedestrians, cars, but no cars, okay? Almost no cars. So you can see that we get very good results here, either with a high K or with a low K. K is the amount of futures you have, okay? So in a data set where social signaling is probably present, we can get an edge on other methods, okay? So one nice thing you can do with this social memory is explainability, okay? To make it explainable, we had to do a little trick. So we had to force the memory to write agents, okay, always in the same portion. Okay, so every time we start the prediction, we fix the region in which agent 0 can write. Okay, so this way we can also try to look where they read. Okay, so please let me use this abuse of language where I say the agent predicts, because it's not the agent predicting anything. You have a neural network that looks at what the agent is doing and forecast its future trajectory. Okay, but in the following slides, I'm going to say the agent reads, meaning that the part of the model that requires to predict agent 0 future location reads the areas of agent 1 or agent 2 and so on. Okay, so by doing this, we can actually have a look at, so this is an example from ETH, and what happens here is that, so these are the real trajectories, this is the observed past and this is the future, okay, so here is the present and this is the future, and we have not predicted yet all this part. So what happens here is that agent 0 here will read either 1 or 2, okay. So at first, agent 0 ignores agent 2. You see the strength of the attention is all into agent 1, okay? And here you see instead the behavior of agent 1, okay? So agent 1 switch the interest, okay? At first, it's interested in both agents, okay? But once it crosses once it gets here, okay, at this point, it's much more important to know what 0 is doing, because it's a possible collision, okay? And of course, this behavior is more evident in our synthetic social agents dataset. So you see here, we have agent 0, which is the red one, that is probably the slowest here. It has to decide who's going to pass first. So at this point in time, which is this image here, it's mostly interested in agent 2, because it's the one that is closest to the center, okay? Because the social rule is, look at the center, who goes there first? If it goes first, I have to stop, and then, okay, so I pay attention to the one that is closest to the center. After he crossed the center, it's not a problem for me anymore. So I switch and I don't pay any more attention to the agent 1, okay? While agent 1 has a similar behavior with respect to the other two agents, okay? So agent 1 reads agent 2, which is the most likely to collide, but after crossing, attention switches, okay? The switch is in this moment here, you see that here we are reading agent 2, because it's the most likely to collide, and then after the crossing, the switch is 1 minute? Wow. 2 minutes, okay, almost done. Okay, so code available, collaborators, almost the same guys as always. Few remarks on foundation models for time series. So I'm going to be a little bit faster here, but the concepts are simpler, okay? So this approach here is very impressive because they use a large language model like GPT to forecast time series, okay? So the idea is to transform the numbers into words, okay? Just by translating the numbers into characters. They do it in a smart way, but still it's just translation of numbers into characters. And then, without retraining the method, okay? Without retraining, so it's a zero-shot forecast, what they do is you know that GPT can sample multiple sentences, okay? So what they do, they sample multiple future outcomes, and then they compute the median as a point estimate, okay? And this works reasonably well, okay? So my colleagues from the telecommunication area in my lab, they wanted to test these ideas in the context of Internet of Everything, okay? Where edge nodes may need to know what is the future state of channels to decide how to reconfigure the network. So what we did is we tested on aqua, ground, and air, and we used these two foundation models for time series. These are specifically designed for time series, so these are not GPT readapted. These are trained on time series. So this stuff exists, and you should use it if you have time series problem, okay? And there are many more nowadays, okay? So what we did is test these two models, and these are behaving similarly to GPT. So they quantize the values, and they predict next tokens. The difference is that this is similarly to GPT, which is fully autoregressive, decoder-only approach, while this is an encoder-decoder approach, okay? So what we observe is that when you have the test domain to shift a lot from the train domain, the zero-shot approach behaves much better, lower error, with respect to fine-tuned models, okay? So these are very powerful models that you can deploy without training at all, okay? And another interesting result is that when you fine-tune the models, of course you get better results, but the interesting thing is that when you fine-tune foundation models and then you use it on a different distribution, they behave better than models that are fine-tuned specifically on the other data. Okay, so the fine-tuning is not destroying and making the forgetting dramatic or catastrophic. Okay, so this is a very interesting result. So, and this was done with Francesco, Benedetta, and Professor Romano Fantacci. Okay, so take-home messages. Okay, so part of this talk was about architectural decisions for forecasting problems, and of course, forecasting means dealing with sequences. So if you do forecasting, you have either a recurrent neural network or a transformer in your architecture. What are the differences? What should you pick? So transformers are good for feature fusion. So if you have a highly multimodal problem, a transformer is very useful to throw into the mix to solve your multimodal problems. But remember that recurrent architectures are coming back. There is Mamba now that has been proposed, and this is because they give you very lean models. And then, in general, like a gated recurrent unit is fairly easy to train, and they are very good at learning the physics of signals. We looked at the memory, which is another way of doing two things. Modeling very complex states, like communication. We can do continual learning with the memory. And in general, it's a way of preserving the long tail, okay? So if your training data has very rare occurrences, a memory is able to memorize an instance of that feature, and you can kind of recover and not forget that kind of information. And finally, a remark on foundation models now are available for images, for video, for language, for image and video, video and language, and so on, and now are also for time series, okay? But what about word foundation models? Okay, so I liked a lot the closing of your talk about the foundation models. So can they help in your word quantities forecasting? I think yes. There are generative word models like Genie, which is able to generate new frames. Also conditioned on some input from the user, okay? So this is a very important tool, and it can be plugged in into forecasting problem probably. But there are also non-generative word models like JIPA from Facebook, from Meta. And I think that this is probably the next brick to put into the house of forecasting. And I think it's all. So these are the references from the work we have seen today. The works that are not from me are in the slides, so if you want to, if you're curious, go into the slides and read the small print. If you have any questions, I don't know if we have time, I can answer. Yeah. No, it's okay.
Because we just gave a quarter of an hour and
yeah, it's okay. Yeah. I talk 50 minutes. It's enough. Okay. Thank you for your time and.